What if we're not alone in the universe? For centuries, humanity has gazed at the stars, haunted by the same tantalizing question. Are we the only ones out here? The Fermi Paradox throws this mystery into sharp relief. With billions of galaxies, trillions of planets, and the sheer age of the cosmos, why haven't we found definitive proof of alien life? Yet the universe is vast, and the clues might already be hiding in plain sight. From eerie UFO sightings to unexplained cosmic signals, the evidence, or lack of it, only deepens the enigma. But what if the answers lie not in fleeting glimpses or conspiracy theories, but in the very fabric of space itself? Across the cosmos, strange and wondrous worlds defy our understanding. Some glow with the faint promise of liquid water, others pulse with bizarre chemical signatures, and a few orbit in the perfect sweet spot for life to thrive. These aren't just specks of light in a telescope, they're potential homes for civilizations beyond our wildest dreams. Imagine oceans hidden beneath icy crusts, vast networks of underground caves, or skies tinged with hues we've never seen. The universe isn't silent, it's whispering to us through these cosmic wonders, inviting us to listen. That's where our journey begins. Today, we're diving into 25 of the most astonishing places in the cosmos where alien life could exist, not as science fiction, but as real, scientifically plausible possibilities. We'll traverse distant exoplanets with atmospheres thick enough to breathe, explore moons where volcanic vents might host entire ecosystems, and even peer into mysterious regions of our own solar system where life could be lurking just beyond our reach. This isn't about little green men or flying saucers, it's about the cutting-edge science that's reshaping how we search for our cosmic neighbors, so buckle up. By the end of this exploration, you'll never look at the night sky the same way again. Beneath the frozen shell of Jupiter's moon, Europa, lies one of the most promising havens for alien life in our solar system. This icy world, slightly smaller than Earth's own moon, hides a secret, a vast global ocean buried under miles of ice, holding more than twice the water of all our planet's oceans combined. Picture an endless, dark abyss, untouched by sunlight for billions of years, yet possibly teeming with life. How could such a place exist so far from the sun's warmth? Europa's ocean stays liquid thanks to intense tidal forces from Jupiter's gravity, which flex and heat the moon's interior, creating the perfect conditions for a hidden aquatic world. Scientists believe this subsurface ocean could resemble Earth's deepest trenches, where hydrothermal vents spew superheated, mineral-rich water into the darkness. On Earth, these vents are oases of life, hosting bizarre creatures like tube worms and extremophile bacteria that thrive without sunlight, drawing energy from chemicals instead. If life exists on Europa, it might cling to similar vents, forming ecosystems unlike anything we've seen. The idea isn't science fiction, it's grounded in real biology. Organisms here wouldn't need photosynthesis. They could survive on sulfur, methane, or other compounds bubbling up from the moon's rocky core. The excitement doesn't end there. Europa's icy crust is crisscrossed with cracks and ridges, suggesting that material from the ocean below might occasionally reach the surface. Some researchers even speculate that plumes of water vapor erupt into space, offering a tantalizing opportunity for future missions to sample the ocean without drilling through miles of ice. Speaking of missions, NASA Europa Clipper is set to launch in the coming years, armed with advanced instruments to map the moon's subsurface, analyze its plumes, and scan for organic molecules. This could be our first real glimpse into whether Europa's dark waters hold the building blocks of life, or perhaps something even more extraordinary. What if we're not just looking for microbes? Europa's ocean has existed for billions of years, longer than many of Earth's ancient seas. That's plenty of time for evolution to work its magic. Could complex organisms swim those depths, adapted to a world without light or surface air? While we don't have answers yet, the possibilities are as vast as Europa's hidden ocean itself. One thing's certain, this small, icy moon might rewrite our understanding of where life can exist and what it might look like. Just beyond Europa's icy allure lies another frozen world with secrets bursting through its surface, Saturn's moon Enceladus. At first glance, this small, gleaming sphere seems too distant and frigid for life, barely 300 miles wide, but appearances deceive. Enceladus isn't just another inert ice ball, it's a cosmic fountain, shooting colossal plumes of water vapor and organic compounds into space from cracks near its south pole. These aren't mere trickles. Cassini, NASA's intrepid spacecraft, witnessed geysers erupting hundreds of miles high, evidence of a hidden ocean churning beneath the ice. What makes these plumes so extraordinary? They're essentially samples delivered straight from Enceladus' subsurface sea to any passing spacecraft. Cassini didn't just photograph them, it flew right through, detecting salts, silica nanoparticles, and molecules like methane and carbon dioxide. These ingredients aren't random, they're the chemical fingerprints of hydrothermal activity, the same processes that fuel life around Earth's deep-sea vents. The ocean below isn't stagnant, it's dynamic, possibly warmed by Saturn's gravitational tug, with vents baking the water to scorching temperatures while minerals dissolve into a briny soup. But the real jaw-dropper, Cassini found molecular hydrogen in those plumes, a gas that on Earth serves as a buffet for microbes thriving in extreme environments. Hydrogen is like a cosmic battery. When it reacts with carbon dioxide, it releases energy life could harness. This discovery turned Enceladus from a curiosity into a frontline contender in the search for alien biology. Imagine a dark, warm ocean, rich in chemicals and bubbling with hydrothermal energy hidden beneath miles of ice. It's not unlike Earth's early oceans where life may have first sparked. The parallels don't end there. Enceladus plumes also contain complex organic molecules, carbon-based compounds that are the building blocks of proteins and DNA. They're not proof of life, but they're the next best thing, a stocked pantry waiting for a chef. And unlike Europa, where we'll need to drill through ice to taste its ocean, Enceladus is practically serving samples on a silver platter. Future missions could fly through its plumes, analyzing them for amino acids or even cellular material. Could something actually live there? The clock has been ticking for billions of years, plenty of time for life to emerge if the conditions are right. Microbes seem plausible, but what if Enceladus' ocean holds surprises? Creatures adapted to eternal darkness, pressure, and chemical feasts. We won't know until we look closer. Thankfully, plans are already underway. Proposed missions like NASA's Enceladus Orbiter aim to orbit this icy moon, sniffing its plumes and even landing near the geysers to hunt for biosignatures. One day, we might crack open Enceladus' icy shell not with drills, but with the moon's own generosity as it flings its secrets into the void. Mars has captivated our imaginations like no other world, not just as a distant red dot, but as a place that may have once mirrored Earth. The evidence is written across its surface: ancient river valleys, dried up lake beds, and mineral deposits that only form in water. These aren't subtle hints, they're geological scars telling a story of a wet, dynamic past. Billions of years ago, Mars may have had rivers carving canyons, lakes pooling in craters, even a vast ocean covering its northern plains. The Perseverance rover has been our latest detective on this case, drilling into rocks that once sat at the bottom of a long-vanished lake. What it found is extraordinary organic molecules, the carbon-based building blocks of life, preserved in Martian mudstone. But water isn't the only clue. Mars' atmosphere holds another tantalizing puzzle: sporadic spikes of methane gas. On Earth, methane is often produced by living organisms, cows, bacteria, even decomposing plants. While geological processes can also create methane, its fleeting presence in the Martian air raises eyebrows. Why does it appear and vanish seasonally? Could subterranean microbes be the unseen architects, thriving in hidden aquifers or deep lava tubes where liquid water might still cling? Some scientists speculate that Mars' subsurface, shielded from harsh radiation and freezing surface temperatures, could harbor resilient microbial colonies even today. The search isn't just about microbes. Human missions to Mars, planned as early as the 2030s, could revolutionize this hunt. Imagine astronauts drilling meters below the surface, exploring ice-rich regions like the poles, or investigating caves where sunlight never reaches. These aren't just expeditions, they're potential first contact scenarios, albeit on a microscopic scale. The implications are staggering. Finding life, even fossilized, would confirm that Earth isn't unique, that life can spark anywhere conditions allow. What if we're too late? Some theories suggest Mars was habitable only briefly before its atmosphere thinned and its water vanished, but even a short window could have been enough. Life on Earth began surprisingly fast after our planet formed. Why not Mars? The answers might lie in samples Perseverance is caching for future return to Earth, or in rovers yet to launch. One thing's certain, Mars isn't just a desert. It's a time capsule holding secrets from an era when two neighboring worlds teemed with the same primordial promise. The question isn't just was there life, it's is it still there, waiting in the shadows? While Mars and Europa dominate discussions of alien life, Saturn's moon Titan is a world that shatters our Earth-centric assumptions. This isn't just another icy satellite. It's a place where rivers carve valleys not with water, but with liquid methane, where dunes stretch for miles made of organic sand, and where the sky is a hazy orange, thick with nitrogen and hydrocarbons. Titan is the only moon in our solar system with a dense atmosphere, one even thicker than Earth's, and beneath that smoggy veil lies a landscape eerily familiar yet profoundly alien. The magic of Titan lies in its chemistry. Here, temperatures plunge to -290 degrees Fahrenheit, so cold that water is frozen solid as rock. But methane and ethane gases on Earth flow as liquids, pooling into vast lakes and seas near the moon's poles. Some of these methane lakes are deeper than the Great Lakes, with waves that might ripple under Titan's low gravity. Could life exist in such a frigid, alien solvent? Scientists call this weird life, organisms not bound by the rules of water-based biology, but instead built to thrive in liquid hydrocarbons. On Earth, extremophiles survive in acid, boiling vents, and even nuclear waste. Why not methane breathers on Titan? The building blocks are already there. Titan's atmosphere is a factory for complex organic molecules, crafting compounds like acetylene and cyanide that rain onto the surface. When NASA Huygens probe landed in 2005, it revealed a world where chemistry never stops. A place where sunlight and cosmic rays constantly rearrange molecules into ever more complex structures. Some researchers believe these processes could mimic Earth's primordial soup, setting the stage for probiotic chemistry, the precursor to life. The question isn't just could life exist here, but how? Would it rely on entirely unfamiliar metabolic pathways, perhaps breathing hydrogen instead of oxygen and consuming acetylene for energy? NASA's Dragonfly mission aims to find out. Slated to launch in 2027, this audacious rotorcraft will soar through Titan's thick air, hopping between sites to sample the surface like a cosmic detective. Dragonfly won't just look for life, it'll hunt for the molecular clues that could reveal how life might emerge in such an environment. Picture a drone skimming over methane lakes, analyzing dunes of organic grains, even listening for the faint chemical whispers of processes we've never imagined. What makes Titan so thrilling isn't just the possibility of life, it's the chance to discover a second Genesis. If life arose independently here, it would prove that biology isn't a fluke of Earth, but a cosmic imperative capable of sparking in the most unexpected places. Titan's methane seas might hold creatures with silicon-based cells or microbial mats floating on hydrocarbon waves. Or perhaps the real treasure is subtler chemical pathways hinting at how life could be, expanding the boundaries of what we consider alive. Either way, Titan isn't just a moon, it's a mirror showing us just how strange and wondrous life might truly be. A mere 4.2 light-years from Earth, nestled in the habitable zone of our nearest stellar neighbor, Proxima Centauri b dangles an irresistible possibility. This could be the first exoplanet where we find life beyond our solar system. Picture a world bathed in the dim crimson glow of a red dwarf star, its skies possibly swirling with alien weather patterns we can barely imagine. But what makes this rocky planet so tantalizing isn't just its proximity. It's the way it defies every assumption we've made about where life can thrive. Proxima Centauri b is tidally locked, meaning one side perpetually faces its star while the other languishes in eternal darkness. At first glance, that sounds inhospitable, a scorching hemisphere baked under constant starlight opposite a frozen wasteland. But nature has a knack for surprises. The Terminator line, that razor-thin boundary between day and night, could be a twilight oasis. Here, temperatures might hover in a Goldilocks zone where liquid water could pool on the surface, sheltered from the extremes. Imagine a planet where the sun never rises or sets, where winds howl between fiery and frozen realms, redistributing heat and creating pockets of stability. Then there's the atmosphere, or the question of whether it even has one. Red dwarfs like Proxima Centauri are tempestuous, frequently unleashing stellar flares that could strip away a planet's protective gases over time. Yet recent simulations suggest Proxima b might cling to a thick, carbon-rich shroud, one that could not only shield the surface but also trap enough heat to melt ice into oceans. Some models even propose a global ocean beneath hydrogen skies, a world where life clings to volcanic archipelagos dotting the eternal twilight. Detecting signs of life here, though, is a puzzle wrapped in cosmic irony. Proxima b is close enough to tantalize but just out of reach for confirmation. Traditional methods like analyzing atmospheric biosignatures require precision beyond our current telescopes, though projects like the James Webb Space Telescope are inching us closer. Imagine the frustration, a potentially habitable world practically next door, and we're stuck squinting at shadows, yet the very challenges inspire innovation. Breakthrough Starshot, a radical initiative, proposes sending featherweight probes propelled by lasers to skim past Proxima b within decades, snapping photos as they zoom by at a fraction of light speed. What if we're not just looking for Earth 2.0? Proxima Centauri b forces us to rethink life's adaptability. Organisms here might photosynthesize infrared light or draw energy from geothermal vents in a starless hemisphere. They could evolve under skies streaked with auroras from relentless stellar winds. The real revelation might not be finding life as we know it, but discovering how little we truly understand about life's potential. Every flicker of data from this enigmatic world whispers the same thrilling question: are we alone, or is our cosmic neighborhood far more crowded than we ever dared to dream? Deep in the constellation Aquarius, 40 light-years from Earth, a tiny star pulses with 7 secrets, the TRAPPIST-1 system. This ultra-cool dwarf, barely larger than Jupiter, hosts a family of planets so tightly packed that standing on one would reveal neighboring worlds hanging in the sky like glowing marbles. Among them, TRAPPIST-1e and F stand out as tantalizing twins, both Earth-sized and cradled in the star's habitable zone where liquid water could exist. But their similarities mask profound differences, making them a cosmic laboratory for testing how alien life might take root under alien suns. TRAPPIST-1e is the inner sibling, a world that might resemble a warmer version of Earth if Earth orbited a star that glowed dim red. Here, the term habitable zone takes on new meaning. The planet receives about the same stellar energy as Earth does from the Sun. but its proximity to its cool host means it's likely tidally locked, with one hemisphere perpetually bathed in faint crimson light while the other faces eternal night. Yet models suggest its atmosphere, if it has one, could redistribute heat, creating a narrow ribbon of temperate climate along the twilight edge. Water here might pool in crater lakes or flow in shallow seas, sheltered from the extremes. The real intrigue, TRAPPIST-1e's density hints at a rocky composition, possibly with an iron core like Earth's, raising the odds of geologic activity and the chemical recycling that fuels life. Then there's TRAPPIST-1f, slightly farther out and cooler, a world where the concept of habitability stretches into the unknown. It basks in about half the stellar energy Earth enjoys, placing it on the outer edge of the habitable zone. If it harbors water, it's likely shrouded under global ice caps with pockets of liquid hiding beneath, like Jupiter's moon Europa. But what if its atmosphere is thick with greenhouse gases? A dense layer of carbon dioxide or methane could trap just enough heat to maintain surface oceans, transforming this distant cousin into a swampy, mist-covered haven. The possibilities don't stop there. TRAPPIST-1f's lower density suggests it might be rich in water, not just on the surface but as a global ocean dwarfing Earth's, capped by a thin crust of ice. The James Webb Space Telescope has already begun peeling back the layers of mystery. Unlike previous instruments, JWST can dissect the chemical fingerprints of these planets' atmospheres as they transit their star. Imagine analyzing starlight filtered through alien skies, hunting for molecules like oxygen, methane, or even industrial pollutants, signposts of biology, or perhaps something unimaginable. Early observations hint that TRAPPIST-1b, the innermost planet, lacks a thick atmosphere likely stripped away by stellar radiation, but E and F, sheltered farther out, remain prime targets. If JWST detects water vapor or an imbalance of gases that can't be explained by geology alone, it could rewrite our understanding of life's cosmic ubiquity. What makes these worlds extraordinary isn't just their potential, it's their proximity to each other. In TRAPPIST-1 compact dance, the planets are so close that panspermia, the ideal life could hitchhike between worlds on asteroids, becomes thrillingly plausible. If life arose on E, could it have seeded F or vice versa? The system might not host one chance for biology, but a shared experiment across multiple planets. Yet challenges loom. Red dwarfs like TRAPPIST-1 are notorious for violent flares, and without robust magnetic fields, these planets' atmospheres could erode over time. Still, life is tenacious. Subsurface oceans or extremophiles clinging to volcanic vents might endure even if the surface is barren. Every new data point from JWST brings us closer to answering the ultimate question. In this miniature solar system, with its stacked Earths and dim red sun, are we looking at cosmic coincidence or the first chapter of a galactic epic? Kepler-186f wasn't just another exoplanet discovery, it was a revelation. Nestled in the constellation Cygnus, 500 light-years away, this unassuming world made history as the first Earth-sized planet ever confirmed in the habitable zone of another star. Picture a place where the sunsets aren't golden but ruby red, cast by the dim glow of its host, a red dwarf barely half the size of our Sun. Kepler-186f's very existence shattered assumptions, proving that planets like ours could orbit stars unlike ours, and igniting a tantalizing question: could life thrive under that crimson light? What sets this world apart isn't just its size, it's the delicate interplay of factors that make it a cosmic cousin to Earth. Kepler-186f is a rocky planet with a radius just 10% larger than our own, suggesting a similar composition of iron and silicate rock. But its orbit is tighter than Mercury's, skimming the inner edge of its star's habitable zone. Here, the term habitable becomes a puzzle. Red dwarfs emit most of their energy as infrared light, far redder and fainter than our Sun's output. For Kepler 186f, this means photosynthetic life, if it exists, would need to adapt to a perpetual twilight, harvesting photons our plants would find useless. Climate models hint at possibilities. A thick carbon dioxide atmosphere could trap enough heat to sustain liquid water, while an ocean-covered surface might distribute warmth, preventing the planet from freezing even under its feeble star. But red dwarfs have a dark side, literally. These stars are notorious for their volatility, unleashing violent flares that can bombard nearby planets with lethal radiation. Kepler 186f star is no exception. Without a robust magnetic field, such flares could strip away its atmosphere over time, leaving the surface exposed to harsh cosmic rays. Yet life might find refuge. Subsurface oceans, shielded by layers of ice or rock, could persist even if the sky above turned hostile. Or perhaps the planet's atmosphere regenerates through volcanic activity, balancing loss with renewal. The extremes of red dwarf systems force us to rethink resilience. Could life on Kepler 186f evolve in fits and starts, surviving in pockets between stellar tantrums? The intrigue deepens when we consider time. Red dwarfs burn so slowly that they'll outlive the universe itself. Kepler 186f has likely existed for billions of years longer than Earth, offering biology an almost unimaginable head start. If life took hold here, it's had epochs to adapt, diversify, even engineer its environment. Imagine ecosystems shaped by eons of flare cycles, or civilizations rising and falling in rhythms we can't fathom. The catch: we're still guessing. Kepler 186f is too distant for our telescopes to analyze its atmosphere directly. Future observatories, like the Habitable Worlds Observatory, might change that, scanning for oxygen or methane, hints of a biosphere at work. Until then, this world remains a beacon, a reminder that Earth's template for life might be just one page in a vast cosmic library. Kepler 186f doesn't just expand the search for aliens, it redefines the very meaning of home. Somewhere in the constellation Cetus, 39 light-years from Earth, a planet named LHS 1140b defies expectations, not as a scorched wasteland or frozen rock, but as a potential water world glimmering beneath an atmosphere thick enough to shield the secrets it may hold. This super-Earth, nearly 7 times more massive than our own planet, orbits a dim red dwarf so faint you'd need a telescope to spot it. But don't let the stars' meek glow fool you. LHS 1140b is anything but ordinary. What makes this world so compelling? Density measurements suggest it's not just a ball of rock it's likely drenched. Models indicate up to 20% of its mass could be water, far more than Earth's measly 0.02%. Imagine a planet where continents, if they exist at all, are mere archipelagos in a global ocean hundreds of miles deep, where the pressure at the bottom crushes water into exotic forms of ice hotter than lava. Yet the real marvel isn't just the water, it's how the planet clings to it. LHS 1140b's thick atmosphere, possibly rich in nitrogen or carbon dioxide, acts like a cosmic pressure cooker, trapping heat and maintaining liquid oceans despite its star's feeble output. But here's the twist: red dwarfs are notorious for spewing deadly radiation, capable of stripping planets bare over time. LHS 1140b's secret weapon might be its sheer bulk. That massive ocean doesn't just hint at habitability, it could be a planetary radiation shield. Water absorbs harmful particles, and a layer this thick might protect any subsurface life from stellar tantrums. Even more intriguing, the planet's gravity could retain a dense atmosphere where lighter gases like hydrogen and oxygen don't simply escape into space. Picture skies choked with mist, refracting the star's crimson light into perpetual twilight, while beneath the waves, hydrothermal vents churn out energy and nutrients, a recipe life has exploited on Earth for billions of years. The next chapter in this mystery belongs to the James Webb Space Telescope and its successors. LHS 1140b is close enough for detailed atmospheric analysis, a rarity among exoplanets. By studying starlight filtering through its skies, astronomers could detect water vapor, methane, or even the asymmetric gas patterns that hint at biological activity. Future ground-based telescopes like the Extremely Large Telescope might go further, mapping temperature variations across the planet's surface, spotting warm currents where life could cluster. Could LHS 1140b be more than a waterlogged curiosity? Its star is ancient, offering biology an extra few billion years to experiment. Life here wouldn't need sunlight. It could thrive on chemical energy from the ocean floor or even harness the faint glow of geothermal vents. The possibilities are as deep as the planet's abyssal seas. One thing's certain, this isn't just another exoplanet. It's a challenge to our assumptions, our technology, and our place in the cosmos. If life can bloom in the crushing dark of a super-Earth's ocean, the universe might be far stranger and far richer than we ever dreamed. Far beyond the familiar planets of our solar system, GJ 1214b drifts through the cosmos like a ghostly enigma, a world so unusual it blurs the line between planet and star. Located 40 light-years away in the constellation Ophiuchus, this steamy mini-Neptune is unlike anything orbiting our Sun. Twice Earth's diameter but nearly 7 times its mass, GJ 1214b belongs to a mysterious class of planets that astronomers are just beginning to understand. What makes it so captivating? Its thick, hydrogen-rich atmosphere swirls with exotic vapors, creating permanent global fog so dense we can't even glimpse the surface below. This isn't just a planet, it's a laboratory for redefining what habitable even means. The first clue to GJ 1214b's strangeness came when scientists tried to peer through its skies. Most exoplanets reveal silhouettes against their host stars, but this world's atmosphere proved nearly opaque, absorbing starlight like a cosmic sponge. Detailed observations showed why high-altitude hazes, possibly composed of salts or hydrocarbon compounds, cloak the entire planet. Imagine a pressure cooker the size of Neptune, where sunlight diffuses into a perpetual, soupy twilight. Surface temperatures likely exceed 300 degrees Fahrenheit, far too hot for liquid water as we know it. Yet within that stifling shroud, something remarkable might be happening. Beneath those layers of hydrogen and haze, GJ 1214b could harbor an ocean unlike any on Earth. Not of water, but of supercritical fluid, a bizarre state of matter where liquids and gases blur together. At extreme pressures, hydrogen forms a hot, dense sea capable of dissolving minerals and organic molecules. Some scientists speculate this environment might mimic Earth's primordial oceans, where life's building blocks first assembled. Others go further, proposing that exotic microbes could evolve to metabolize hydrogen, thriving without oxygen or sunlight in a biochemistry we've never imagined. The debate hinges on depth. If GJ 1214b's atmosphere extends hundreds of miles before transitioning to solid ground, life seems improbable. Just too much crushing gas, not enough stable chemistry. But if the haze is shallow, covering a rocky core with manageable pressures, the odds shift. Hydrothermal vents on such a world could pump out energy and complex molecules, creating niches for extremophiles. There's precedent. In Earth's deepest trenches, organisms survive by eating hydrogen seeping from volcanic cracks. Scale that up to a planet-wide system, and suddenly GJ 1214b's hellish exterior might hide pockets of possibility. What truly excites astronomers isn't just whether life exists here. It's how this planet shatters our Earth-centric biases. By conventional standards, GJ 1214b is a nightmare. No solid surface, no sunlight, no oxygen. Yet nature constantly proves more inventive than our assumptions. If life can emerge in such a place, it suggests the universe teems with diversity far beyond the familiar. Future telescopes like NASA's Habitable Worlds Observatory might finally pierce GJ 1214b's haze, searching for chemical imbalances that hint at unseen activity below. Until then, this steamy mini-Neptune remains a cosmic Rorschach test, challenging us to reconsider not just where life might exist, but what life could even be. K2-18b hangs in the cosmos like a celestial mirage, 120 light-years away, a world that shouldn't exist by old rules, yet defies them with breathtaking audacity. Discovered by NASA Kepler spacecraft in 2015, this super-Earth, nearly 9 times our planet's mass, initially seemed like just another gas-shrouded orb. Then came the Hubble data. In 2019, astronomers did the unthinkable. They detected water vapor swirling in K2-18b's atmosphere, marking the first time water had ever been confirmed on a habitable zone exoplanet. But this isn't a story of familiar oceans under blue skies. K2-18b belongs to a hypothetical class called Haitian worlds, planets with hydrogen-rich atmospheres towering over global liquid water oceans, a configuration once dismissed as too extreme for life. The Haitian hypothesis flips traditional astrobiology on its head. Picture an Earth-sized core wrapped in an atmosphere so thick with hydrogen it extends hundreds of miles skyward, creating pressures unimaginable on our planet. Yet beneath this crushing blanket, something miraculous might occur. The hydrogen could act like a cosmic pressure cooker, trapping enough heat to maintain liquid oceans despite the planet's distance from its dim red dwarf star. On K2-18b, these oceans wouldn't hug the surface. They'd be buried under layers of gas, possibly tens or hundreds of miles deep, kept liquid not by sunlight but by geothermal warmth and atmospheric insulation. The term ocean barely does it justice. This would be a realm where water exists in a perpetual twilight, shielded from stellar flares but bubbling with energy from the planet's molten interior. What makes K2-18b a biosignature goldmine isn't just the water, it's the atmospheric chemistry. Hydrogen-dominated atmospheres are surprisingly transparent to certain light wavelengths, allowing telescopes like James Webb to peer deeper than usual. When scientists analyzed starlight filtering through K2-18b's skies, they spotted not just water vapor but also tantalizing hints of dimethyl sulfide, a compound on Earth produced only by living organisms, particularly phytoplankton. The detection remains unconfirmed, but the mere possibility sent shockwaves through the scientific community, a Haitian world with oceans and potential biosignatures. It's like finding a rainforest hidden beneath a desert's dunes, yet the challenges are as stark as the promise. Red dwarfs like K2-18b's host star are prone to violent flares, and without a magnetic field, the planet's atmosphere could be slowly eroded. Even if life exists, it would face staggering pressures and a water column so dense it might form exotic ices near the ocean floor. But extremophiles on Earth thrive in deep sea vents and acidic hot springs. Why not here? The ocean's sheer depth could create multiple habitable layers with organisms adapted to different pressures and chemistries. Some might metabolize hydrogen, others feed on organic rain from the atmosphere above. The next steps hinge on cutting-edge technology. James Webb's follow-up observations could confirm dimethyl sulfide or detect other biomarkers like methane and oxygen imbalances. Future telescopes might even map temperature variations, revealing ocean currents or hotspots of activity. K2-18b isn't just a scientific target, it's a test of our imagination. If life can flourish under a hydrogen sky, in oceans without shores or sunsets, then the universe's palette for biology is far broader than we ever dared to dream. Every new datum from this enigmatic world whispers a revolutionary truth. The search for aliens isn't about finding Earth 2.0. It's about discovering life as we don't know it. 12 light-years away, hidden in the constellation Aries, a small red dwarf named Tegodon star burns so faintly it wasn't even discovered until 2003. But this cosmic afterthought holds a staggering secret: two Earth-sized planets, Tegodon star B and C, orbiting so perfectly they've rewritten the rules of where life might thrive. These aren't just any worlds, they're among the most Earth-like exoplanets ever found, with surface temperatures that could allow liquid water to pool without boiling or freezing. What makes them extraordinary isn't just their location in the habitable zone, it's the quiet serenity of their tiny, ancient star. Tegodon star is a vampire's dream, cool, dim, and incredibly stable. Unlike the violent red dwarfs that blast their planets with deadly flares, this star hums along with barely a flicker, offering its planets a rare gift: billions of years of gentle, unchanging light. For context, our Sun has only existed for 4.6 billion years. Tegodon star could be twice as old, meaning its planets have had twice as long for life to emerge, evolve, and possibly even master its environment. Imagine civilizations rising under endless twilight skies, their history stretching back further than Earth's entire geologic record. The inner planet, Tegodon B, orbits every 4.9 Earth days, basking in warmth that might mirror Mediterranean climates. Climate models suggest it could maintain surface temperatures around 28 degrees Celsius, balmy by Earth standards, if it has an atmosphere similar to ours. But here's the twist: red dwarf planets often lose their atmospheres to stellar winds unless they have strong magnetic fields or thick carbon dioxide shrouds. Tegodon B's saving grace might be its presumed geology. If it's volcanically active like Earth or Jupiter's moon Io, it could continuously replenish its atmosphere, creating a self-sustaining cycle. Then there's Tegodon C, slightly farther out and cooler, with an 11-day year. Estimates place its equilibrium temperature near -47 degrees Celsius, too cold for liquid water, unless greenhouse gases like methane or nitrogen warm it beyond expectations. This is where the surprises begin. On Earth, subsurface lakes thrive beneath Antarctica's ice at similar temperatures, heated by geothermal activity. If Tegodon C has a rocky core simmering with radioactive decay or tidal heating, its icy shell might conceal hidden oceans, much like Europa or Enceladus in our solar system. The real magic lies in their potential climates. Most exoplanets around red dwarfs are tidally locked, with one side perpetually scorched and the other frozen. But Tegodon's planets orbit just far enough to possibly avoid this fate, instead rotating slowly to create day-night cycles. Combined with an atmosphere, this could distribute heat more evenly, preventing the extremes that make other red dwarf worlds hostile. Some simulations even suggest Tegodon B might have stable weather patterns: clouds, rain, perhaps even seasons if conditions align. Yet the greatest enigma is time. These planets are ancient, possibly 8 to 10 billion years old. That's enough time for life to have arisen, been wiped out by cosmic events, and arisen again multiple times. If intelligence evolved here, it could be staggeringly advanced compared to humanity. Or life might have adapted to changes we can't fathom, thriving in ways that defy Earth's biology. Detecting signs of life, however, remains a challenge. Tegodon's star is dim, making atmospheric studies difficult even for telescopes like James Webb. But future instruments like the European Extremely Large Telescope could analyze starlight filtering through these planet skies, hunting for oxygen, methane, or other biosignatures. One tantalizing possibility: if Tegodon B has lush vegetation adapted to infrared light, its surface might reflect a unique red edge signature, a fingerprint of alien photosynthesis. What lingers is the profound implication. Tegodon's planets aren't just potential homes for life, they're time capsules offering a glimpse into how biology might evolve given near eternity to experiment. Whether they're verdant paradises or frozen vaults holding primordial secrets, these worlds remind us that life's canvas might be far vaster and far stranger than we've dared to paint. Just 13.8 light-years away, practically, our cosmic backyard, Wolf 1061c, spins in a precarious dance with its dim red dwarf star. This super-Earth, nearly 4 times our planet's mass, isn't just another rocky world. It's a study in extremes where gravity bends the rules of habitability and seasons swing between scorching heat and frigid darkness. What makes Wolf 1061c so fascinating isn't just its size or proximity, it's the way it forces us to rethink what survivable even means in the cosmos. First, the gravity. With nearly twice Earth's pull, this planet's dense grip could be its greatest ally. A thicker atmosphere might cling to its surface, resisting the stripping effects of stellar winds that plague other red dwarf worlds. Picture skies so dense they act like a thermal blanket, redistributing heat from the star-facing side to the frozen shadows, possibly creating pockets of temperate stability. But that same gravity comes with a price. Walking here would feel like carrying an extra person on your back, and native life, if it exists, would need sturdy biology to withstand the constant crush. Think compact, low-profile organisms, perhaps with reinforced cellular structures or hydraulic support systems unheard of on Earth. Then there's the orbit, a wobbly, elliptical path that sends the planet surging close to its star before retreating into the cold. Unlike Earth's gentle seasons, Wolf 1061c's climate swings could be apocalyptic. During its summer, the star looms large, bathing one hemisphere in relentless infrared glare. Then, as it pulls away, temperatures plummet, locking vast regions in ice. Survival here would demand radical adaptations. Organisms might hibernate underground during extremes, or evolve rapid life cycles to bloom in brief windows of mild weather. Some scientists speculate about shadow biomass ecosystems clinging to twilight zones where temperatures balance between fire and ice, or even migratory life forms that follow the shifting habitable belt like cosmic nomads. The star itself adds another twist. Wolf 1061 is calmer than most red dwarfs, but it still flickers with occasional flares. Any atmosphere would need to weather these storms without dissolving into space. Remarkably, the planet's location near the inner edge of the habitable zone might help. The extrastellar heat could keep its oceans liquid even under a hydrogen-rich atmosphere, while volcanic activity fueled by gravitational flexing might replenish atmospheric gases faster than the star can strip them away. Could life thrive here? It's a gamble. On one hand, extremophiles on Earth prosper in boiling geysers and Antarctic brine, proving biology's knack for exploiting niches. On the other, Wolf 1061c's violent rhythms might reset the clock too often for complex life to gain a foothold. But if life does cling on, it could be unlike anything we know, slow-growing, hyper-resilient, and tuned to the planet's deep gravitational hum. Future telescopes might glimpse its atmosphere, hunting for chemical imbalances that betray hidden activity. Until then, this super-Earth stands as a test, not just of life's adaptability, but of our own imagination. 44 light-years from Earth, in the constellation Pictor, a planet named HD 40307G defies the tidy circles of our solar system. This super-Earth, nearly 7 times as massive as our home planet, follows a path few worlds dare, an oval-shaped orbit that swings it from cozy warmth to biting cold with each passing year. Yet here's the twist: despite this cosmic roller coaster, HD 40307G sits snugly in its star's habitable zone, a region where liquid water could exist. It's a paradox, a world caught between extremes, yet potentially balanced just right for life to cling on. The key lies in its star. HD 40307 is an orange dwarf, slightly cooler and smaller than our Sun, but far calmer than the flare-prone red dwarfs that dominate exoplanet discoveries. This stability offers HD 40307G a fighting chance. Unlike planets hugging volatile stars, this world's atmosphere might survive intact over billions of years, shielding any potential oceans from evaporation or freeze out. But that elongated orbit introduces a wild card: seasons unlike anything on Earth. Picture a year where summers blaze under double the stellar heat, while winters plunge into prolonged twilight. If Earth's seasons are gentle waves, HD 40307Gs are tidal forces, reshaping the planet's climate in dramatic cycles. How could life endure such swings? The answer might lie beneath the surface. A rocky planet this massive likely harbors intense volcanic activity, fueled by gravitational friction from its lopsided orbit. Underground heat could maintain vast aquifers or lava tubes where organisms hunker down during climatic extremes, emerging only during temperate transitions. Alternatively, a thick atmosphere might smooth out the variations, redistributing heat through relentless wind patterns. Imagine jet streams whipping across continents at hurricane speeds, or algae blooms exploding across oceans as sunlight returns after a long winter. The real intrigue: HD 40307G's sheer age. At over 1 billion years older than Earth, this planet has had ample time for life to adapt or to rise and fall multiple times. Evolutionary paths here could be stranger than fiction. Perhaps organisms sync their life cycles to orbital rhythms, lying dormant for decades before erupting into frenzied activity. Or maybe entire ecosystems migrate across latitudes, chasing the shifting Goldilocks zone like cosmic nomads. For now, mysteries linger. Current telescopes can't directly observe HD 40307G's atmosphere, but future instruments might sniff out water vapor or methane hints of hidden processes. Until then, this eccentric world stands as a reminder: habitability isn't about perfection. It's about resilience. In the grand cosmic dance, HD 40307G waltzes to its own chaotic tempo, and life, if it's there, has learned to keep time. Gliese 581G isn't just a planet, it's a cosmic controversy. Discovered in 2010 orbiting a dim red dwarf 20 light-years away, this super-Earth sent shockwaves through astronomy when researchers announced it sat squarely in the habitable zone, with temperatures that could allow liquid water. The media hailed it as the first true Goldilocks planet, not too hot, not too cold, but just right for life. But within months, other astronomers challenged the discovery, igniting a debate that still smolders today. What makes this world so contentious isn't just science, it's the tantalizing possibility that we might have glimpsed our cosmic twin, only to have it slip through our fingers. The case for Gliese 581G hinges on meticulous data. Using the radial velocity method, scientists tracked subtle wobbles in the star's motion, suggesting the gravitational tug of 6 planets. The fourth planet out, Gliese 581G, appeared to have a 37-day orbit, placing it perfectly for liquid water, assuming it had an Earth-like atmosphere. Its estimated mass, 3 to 4 times Earth's, hinted at a rocky composition, while its gravity, around 1.1 to 1.7 times Earth's, might be survivable for humans. The real clincher: models suggested it could be tidally locked yet still habitable, with a twilight belt where temperatures balanced between scorching days and frozen nights. But skepticism erupted almost immediately. Other teams reprocessing the same data found no clear signal for Gliese 581G, arguing the supposed planet might be noise, an artifact of stellar activity masquerading as a world. Red dwarfs like Gliese 581 are notoriously turbulent, with sunspots and flares that can mimic planetary tugs. Without direct imaging or transits, the planet's existence hinged on statistical interpretations. Even the original discoverers admitted the signal was faint, buried in a complex system with multiple overlapping orbits, yet the intrigue persists. Why? Because Gliese 581g represents a tipping point in exoplanet science, its disputed status forces us to confront the limits of our technology, how we hunt for worlds at the edge of detectability. Future telescopes like the Extremely Large Telescope could settle the debate, either confirming the planet or relegating it to a cautionary tale. But the deeper lesson lies in what Gliese 581g symbolizes: our desperation to find Earth analogues even when evidence hangs by a thread. What if it does exist? Picture a world where the sun never moves in the sky, where glaciers creep into eternal twilight, and rivers might flow beneath a thick, heat-trapping atmosphere. If life took root there, it would face brutal challenges: stellar flares, gravitational stresses, possible volcanic upheavals. But extremophiles on Earth thrive in undersea vents and acidic springs, proving life's tenacity. Gliese 581g, real or not, taught us something profound. The line between discovery and delusion is as thin as the data we dare to interpret. And in that ambiguity, the hunt for another Earth grows ever more thrilling. Kepler 442b isn't just another exoplanet, it's a cosmic mirror reflecting Earth's potential in a way few worlds can. Orbiting a modest orange dwarf star 1,200 light-years away, this rocky planet stands out with an Earth similarity index of 0.84, one of the highest ever recorded. What does that number really mean? Imagine a world where gravity feels almost familiar, just 20% stronger than ours, and where the landscape might include rolling plains, craggy mountains, or even vast oceans. But the real magic lies in the light. Kepler 442b receives about 70% of the sunlight that bathes Earth, comparable to early evening on a summer day. Not too dim for photosynthesis, not too harsh for delicate biochemistry. For life as we know it, this is as close to a sweet spot as the universe has offered so far. Yet the planet's star holds the most tantalizing clue of all. Unlike our middle-aged sun, Kepler 442's host is older, possibly billions of years further along in its lifespan. Why does that matter? Time is evolution's greatest ally. On Earth, life needed nearly 4 billion years to progress from single-celled organisms to spacefaring civilizations. An older star means a head start. Picture a world where life has had extra eons to experiment, where complex organisms might have evolved through cycles of extinction and renewal we can barely fathom. Forests could have risen and fossilized a dozen times over. Civilizations might have emerged, flourished, and vanished long before humans even walked our own planet. The climate here is a fascinating puzzle. With an orbit slightly longer than Earth's year, seasons would unfold at a leisurely pace, stretched over months of gradual change. The planet's axial tilt, if it has one, could create milder winters and summers than ours, minimizing extreme weather. But the real wildcard is the star's orange glow. Plants on Kepler 442b, should they exist, might evolve to harness more infrared light, painting their foliage in deep purples or blacks to absorb every possible photon. Oceans would shimmer under a peach-colored sky, their waves churned by winds slower yet more persistent than Earth's due to the planet's higher density. What truly sets this world apart isn't just its specs, it's the convergence of factors that align so neatly with life's requirements. Magnetic field models suggest it could retain a robust atmosphere despite stellar winds. Geologic activity might recycle carbon, stabilizing temperatures over eons. Even its position in the galaxy is optimal, far enough from the crowded core to avoid lethal radiation, yet close enough to be seeded with heavy elements from ancient supernova. Kepler 442b isn't just a candidate for habitability, it's a masterclass in how many variables can align to create a living world, the bittersweet reality. We may never see it directly. At its current distance, even next-generation telescopes will struggle to resolve its atmosphere. But as we catalog more worlds like this, patterns emerge. Kepler 442b is proof that Earth isn't a fluke. It's a template the universe enjoys repeating, and somewhere beneath that alien sun, life might already know what we're just beginning to understand, that across the cosmos, the ingredients for existence are waiting, patient and abundant, for the right conditions to stir them awake. Pulsars aren't just cosmic lighthouses, they're graveyards boasting some of the strangest real estate in the universe. Take PSRB 1257+12, a millisecond pulsar over 2,000 light-years away, spinning nearly 10,000 times faster than a kitchen blender. This stellar corpse shouldn't have planets at all. When its progenitor star went supernova, the explosion should have vaporized everything in its vicinity. Yet against all odds, two survivors cling to this dead star, PSRB 1257+12b and c, worlds born from stellar apocalypse with compositions that defy imagination. Imagine planets forged in the crucible of a supernova's fury. Their surfaces aren't rock or gas, but something far more exotic, crystalline carbon compressed into structures resembling cosmic diamonds. These aren't the gemstones you'd find in a jewelry store. They're ultra-dense, metallic forms of carbon that might extend hundreds of miles below the surface, forged under pressures that would crush Earth's core into paste. The pulsar's relentless radiation bathes them in high-energy particles, creating surface temperatures hot enough to melt lead on the sunlit side, while the dark side freezes near absolute zero. If hell had a postal code, it might be here. Yet where science sees a wasteland, astrobiologists see possibility. Life here wouldn't resemble Earth's biology. It would be something far stranger. Picture organisms with cells made of silicate cages, their metabolisms powered not by sunlight or organic chemistry, but by the pulsar's own radiation. These hypothetical extremophiles might harvest energy directly from the star's particle wind, using nuclear interactions rather than molecular bonds. Their biochemical machinery could rely on nuclear isomers, exotic atomic configurations that release energy when they decay. In this nightmare environment, DNA would be shredded in seconds, so evolution might favor something far more robust. Life forms built around fractal patterns in solid-state materials, growing and reproducing through quantum tunneling effects in their diamond-like matrices. The clock is literally ticking for these worlds. PSRB 1257+12 spin is gradually slowing, its radiation field weakening over millennia. Any life here would race against time, adapting to ever-dwindling energy sources before their world becomes too cold even for nuclear-powered biology. Some theories suggest such organisms might migrate underground, tapping into residual heat from the planet's radioactive core, or even learn to manipulate the pulsar's magnetic field to siphon energy more efficiently. The real wonder isn't whether life exists here, it's that these planets exist at all. They're cosmic phoenixes rising from the ashes of a star's self-destruction. Future telescopes might detect subtle infrared glows from their surfaces, hints of thermal vents or crystalline forests capturing pulsar energy. Until then, they stand as monuments to nature's creativity, proof that even in the universe's most hostile corners, the ingredients for existence, in forms we're only beginning to imagine, might still find a way. TOI 700d sits just 100 light-years away, a silent beacon in the constellation Dorado, one of the few Earth-sized planets we found orbiting squarely in its star's habitable zone. But this isn't just another exoplanet. What makes it extraordinary is its host, a serene M-dwarf star so calm and steady, it barely flickers. Unlike the violent flares of other red dwarfs that scorch nearby worlds, TOI 700 hums like a cosmic lullaby, offering its planets a rare gift: stability. The planet's dance with its star is locked in a gravitational embrace, one side forever bathed in dim crimson light, the other shrouded in eternal night. Synchronous rotation might sound like a death sentence for habitability, but TOI 700d defies expectations. Climate simulations reveal something astonishing. thick, reflective clouds could form on the star-facing side, acting like a planetary sunshade. These aren't just any clouds, they're potential climate engineers, bouncing enough heat back into space to prevent the day side from boiling over while circulating warmth toward the frigid dark side. Imagine a world where hurricane force winds endlessly redistribute heat, creating a twilight belt where temperatures hover just right for liquid water to pool. NASA test telescopes spotted this world by the faintest dip in starlight, a telltale blink lasting just 53 minutes every 37 Earth days. But the real magic lies in the details. TOI 700d is only 20% larger than Earth, with a likely rocky composition and gravity close enough to ours that walking there wouldn't feel alien. Its star's gentle glow means photosynthesis, if it exists here, would need to adapt to infrared light, painting hypothetical forests in deep burgundies and blacks. The planet's true test is water. Without oceans, even the perfect orbit means nothing. But models suggest TOI 700d could be a Hycean world, a term blending hydrogen and ocean, where a thick atmosphere traps enough heat to sustain global seas beneath hydrogen-rich skies. Or perhaps it's more familiar with continents and weather cycles echoing Earth's, just slower and steadier under that eternal sunset. Future telescopes like HAB-X or LUVOIR could analyze its atmosphere for water vapor, methane, or even oxygen, chemical whispers of life. For now, TOI 700d remains a tantalizing what-if, a reminder that sometimes the most promising worlds aren't the flashiest, just the ones patient enough to wait for us to find them. WASP-90 floats through space like a celestial cotton candy, a gas giant so puffed up its density rivals that of styrofoam. 750 light-years away in the constellation Phoenix, this world defies expectations with an atmosphere so sodium-rich it scatters starlight into prismatic hues, earning it the nickname the Fluffy Planet. But beneath its cotton-soft exterior lies a brutal reality. Surface temperatures soaring over 1,000 degrees Celsius, where metals vaporize and life as we know it dissolves into the scorching winds. Yet WASP-90's true significance isn't about itself, it's about the cosmic real estate it represents. Just as Jupiter's moons transformed our understanding of habitable zones, this bloated giant whispers a provocative question: could its own moons harbor secrets too? Picture a moon skimming the outer edges of WASP-90's gravitational embrace, shielded from the star's wrath by the planet's bulk. While the gas giant broils under relentless radiation, its satellites might linger in a delicate balance far enough to avoid sterilization, yet close enough to bask in reflected heat. Jupiter's icy Europa and volcanic Io prove that tidal forces can sculpt worlds beyond imagination, kneading their interiors into geysers and subsurface oceans. Apply that logic here. A moon with a thick atmosphere could trap geothermal warmth from constant gravitational flexing, creating lakes of liquid water or even hydrocarbon seas like Titan's. The ingredients are tantalizing. WASP-90's extended atmosphere, rich in sodium and potassium, might seed its moons with exotic salts compounds that could lower the freezing point of water or catalyze bizarre chemistries in hidden aquifers. But the real magic lies in the shadows. A moon orbiting WASP-90 could experience eternal eclipses, its days punctuated by hours plunged behind the planet's gauzy veil. These periods of darkness might act as a natural thermostat, cooling the surface just enough to condense atmospheric moisture into rain or snow. Imagine a world where the sky periodically dims to a deep amber as the sodium haze filters sunlight, casting everything in a surreal, sepia-toned glow. Organisms here might evolve to sync their metabolisms with these eclipses, flowering in brief windows of milder temperatures before retreating into dormancy. The challenge detecting such moons is beyond current technology. WASP-90's bloated silhouette already dwarfs most stars during transit. Spotting a moon's minuscule dip in light would be like hearing a whisper in a hurricane. Yet future observatories like the European Extremely Large Telescope could hunt for gravitational wobbles, telltale tugs from unseen satellites. Until then, we're left with celestial poetry, a hostile giant, its very strangeness painting visions of sheltered oases where life might cling in the unlikeliest of corners. The universe has a habit of surprising us, and WASP 96b is no exception, a reminder that sometimes the most promising real estate isn't the planet itself, but the worlds it might cradle in its grasp. At the heart of our galaxy, where stars crowd together like fireflies in a jar, lies a monster Sagittarius A, the supermassive black hole anchoring the Milky Way. This isn't just a cosmic vacuum cleaner, it's the engine of a region so extreme it redefines the very meaning of habitable. Picture a place where stars are packed 1,000,000 times tighter than in our solar neighborhood, whipping around at blinding speeds, their light warped into eerie halos by gravitational forces we can barely comprehend. The Galactic Center is a maelstrom of radiation, tidal forces, and chaotic orbits, yet hidden in this chaos, some scientists believe, might be the ultimate crucible for life unlike anything we've imagined. The sheer density of stars here creates staggering possibilities. With so many suns crammed into such a small space, planetary systems could intersect, their gravitational dances kicking rogue worlds into strange new orbits. Imagine a planet not bound to any one star, but wandering through this stellar jungle, warmed by the collective glow of thousands of nearby suns. It's a scenario where the night sky would blaze with constellations 100 times brighter than our full moon, casting permanent twilight over rugged landscapes. But the real magic lies deeper, where civilizations, if they exist, might have tapped into Sagittarius itself. Black holes aren't just destructive, they're cosmic power plants. Advanced beings could theoretically harness their energy through mechanisms like the Penrose process, extracting power from the black hole's spinning ergosphere. Picture Dyson spheres not around stars, but around the event horizon, capturing the intense radiation and plasma jets shooting outward. Or perhaps civilizations here have mastered the art of black hole agriculture, using the extreme gravity to slingshot stars closer, creating a rotating menu of energy sources. The Galactic Center wouldn't just be their home, it would be their fuel depot, their engine room, their grandest tool. Then there's life in the shadows. Radiation-resistant organisms might evolve in the thick atmospheres of planets shielded by magnetic fields, or deep beneath icy crusts where stellar flares can't reach. On Earth, we've found microbes thriving in nuclear reactor cores, proof that life can adapt to the harshest energy floods. Near Sagittarius A, evolution could have taken this resilience to unimaginable extremes, crafting creatures that don't just survive high-energy environments but thrive on them, metabolizing X-rays or cosmic rays the way Earth's plants use sunlight. But the greatest enigma remains time. The Galactic Center is ancient, with stars billions of years older than our Sun. Any civilization here would have had epochs to refine their understanding of physics, transform their environment, or even transcend biology itself. They might view our corner of the galaxy as a quiet backwater, their communications pulsing in frequencies or dimensions we're only beginning to theorize. The paradox: we're listening. Projects like Breakthrough Listen scan the Galactic Center for technosignatures, narrowband radio signals, laser pulses, or even Dyson swarm heat signatures. Yet if advanced life exists there, it may operate on principles so foreign we're like ants trying to decode Wi-Fi. The silence isn't proof of absence, it's a challenge to expand our imagination. The Galactic Center doesn't just test the limits of life, it forces us to question what life could become when forged in the universe's most extreme crucible. Rogue planets drift through the galaxy like cosmic orphans, worlds torn from their star systems by gravitational chaos, left to wander the eternal dark. But don't mistake their solitude for emptiness. These nomads might outnumber stars in the Milky Way by a staggering margin, with estimates suggesting billions could be lurking unseen in the void. What makes them fascinating isn't just their abundance, it's the audacious possibility that life, against all odds, might have hitched a ride on these lonely travelers. Picture a rogue planet ejected from its cradle in some ancient stellar skirmish, now cruising through interstellar space with no sun to warm its surface. Temperatures should plunge near absolute zero, freezing any hope of biology except nature has workarounds. Some of these worlds could cling to thick hydrogen atmospheres, acting like cosmic pressure cookers that trap geothermal heat seeping from radioactive cores. Imagine vast underground oceans kept liquid by the planet's inner warmth, shielded from the void by miles of ice or dense atmospheric layers. Hydrothermal vents on Earth's ocean floor thrive without sunlight, powered by chemical reactions between water and rock. On a rogue planet, such vents could sustain entire ecosystems in perpetual darkness, fueled by the slow decay of uranium and thorium in the planet's belly. Then there's the wild card, tidal heating. Some rogue planets might still host moons, their gravitational dances generating friction that warms both worlds from within. Europa's subsurface ocean exists because Jupiter's gravity needs its core. Why couldn't a moonless rogue planet with a slightly elliptical orbit do the same to itself? The resulting heat could maintain liquid water pockets for billions of years, long enough for life to emerge and adapt to the endless night, the real shocker. These worlds might be more hospitable than planets orbiting stars. No flares, no ultraviolet radiation, no scorching solar winds, just serene, stable environments where life could evolve without cosmic tantrums disrupting the peace. Some models even suggest rogue planets with hydrogen-rich atmospheres could create a greenhouse effect strong enough to maintain surface temperatures above freezing, despite the lack of starlight. Lakes of liquid water might persist under alien skies tinged pink by atmospheric chemistry, illuminated only by the faint glow of distant nebulae. Detecting these wanderers is a nightmare. They emit no light and reflect none. But gravitational microlensing surveys and next-generation telescopes like Nancy Grace Roman might catch their silhouettes as they drift between stars. The bigger question is what we'd find if we could land there. Microbial extremophiles, complex organisms adapted to slow metabolisms in near-frozen seas. Or something entirely unimaginable, thriving on energy sources we've yet to conceive. Rogue planets force us to rethink life's limits. They're the ultimate survivors, carrying the potential for biology into the deepest, darkest reaches of the galaxy. If life exists on even a fraction of them, the universe might be far more alive and far stranger than we ever dared to guess. Beneath Titan's methane rivers and hydrocarbon dunes lies an even greater mystery, a global ocean of liquid water, locked away under an icy shell that could be miles thick. This isn't just a slushy layer, it's a vast, salty sea, potentially 10 times deeper than Earth's Mariana Trench, with enough volume to rival our own planet's surface oceans. What makes this subsurface realm so tantalizing isn't just the water. It's the extraordinary chemistry unfolding where this ocean meets Titan's exotic organic surface. Picture a boundary zone where liquid water, seeping through fractures in the ice, interacts with lakes of methane and ethane, creating a molecular playground unlike anything in our solar system. Here, the rules of life as we know them bend. Earth's biology relies on water as a solvent, but Titan's ocean might share its stage with hydrocarbon solvents, enabling reactions that would be impossible in our own seas. When water molecules meet methane under high pressure, they can form crystalline structures called clathrates, ice-like cages that trap gas molecules inside. These aren't just geological curiosities. They could act as chemical factories, concentrating organic compounds and providing sheltered microenvironments where primitive life might emerge. Imagine microbes with cell membranes made not of lipids like Earth's organisms, but of acrylonitrile, a molecule already detected in Titan's atmosphere, capable of forming stable, flexible structures in liquid methane. The energy question is even wilder. Without sunlight, life in Titan's ocean would need alternative fuel sources. Hydrothermal vents, driven by the Moon's gravitational tug-of-war with Saturn, could pump heat and minerals into the water just as they do on Earth. But there's a twist. Titan's ocean might also contain ammonia, lowering the freezing point and creating a briny cocktail where chemical reactions unfold more sluggishly, yet no less potently. Slow doesn't mean sterile. Some organisms could exploit redox reactions between hydrogen and acetylene, a compound raining down from Titan's skies, metabolizing it much like Earth's deep-sea microbes breathe sulfate. The most electrifying possibility, Titan's ocean and surface might not be separate worlds. Cryovolcanoes could erupt, spewing water from the depths into the Moon's methane lakes, creating fleeting oases where water-based and hydrocarbon-based chemistries collide. In these transient zones, hybrid life forms might thrive, organisms capable of switching between solvents or even harnessing both. It's a scenario that challenges every assumption about biology's boundaries. NASA's Dragonfly mission will land on Titan in the 2034, but it won't reach the ocean. The real breakthroughs may come from future probes, submersibles designed to melt through the ice, or drones that sample plumes at the poles. Until then, Titan's hidden sea remains a cipher, whispering a provocative truth. Life might not need a sunlit surface to flourish. Sometimes the most promising frontiers are the ones buried in eternal shadows. Europa's plumes aren't just geysers, they're golden tickets to an alien ocean, spewing frozen droplets of the Moon's hidden seas straight into space. Picture a cosmic fountain, erupting from cracks in the ice with such force that material reaches heights of over 100 miles, creating a fleeting but precious opportunity. Sampling Europa's subsurface without drilling through miles of frozen crust. This isn't science fiction. NASA's upcoming Europa Clipper mission is designed to do exactly that, armed with instruments capable of analyzing these plumes for the holy grail of astrobiology, organic molecules, amino acids, or even fragments of cellular material. The parallels to Enceladus are impossible to ignore. Saturn's icy moon proved plume sampling works when Cassini flew through its jets, detecting salts, silica, and molecular hydrogen, clear signs of hydrothermal activity. But Europa's plumes are trickier. They are intermittent, unpredictable, and embedded in Jupiter's punishing radiation belts, which can fry sensitive instruments. Unlike Enceladus's consistent eruptions, Europa's seem tied to tidal flexing, flaring up when gravitational stresses crack the ice shell open. Timing a spacecraft's flyby is like trying to catch lightning in a bottle. Yet the payoff could be revolutionary. Europa's ocean is older and far larger than Enceladus's, with more time and space for complex chemistry and potentially biology. The plumes likely carry material from the seafloor, where hydrothermal vents might be churning out nutrients. If amino acids swirl in those icy particles, they'd be the clearest sign yet that Europa's ocean is doing more than just existing, it's building the ingredients for life. And if, by some cosmic stroke of luck, those plumes contain actual cellular debris, even fossilized, it would rewrite our understanding of life's ubiquity in the universe. The challenge lies in detection. Europa Clipper's mass spectrometers will vaporize plume particles, breaking them down into their chemical components. Like cosmic detectives, scientists will look for patterns, ratios of carbon isotopes, phosphorus concentrations, or molecular structures that mirror earthly biology. But Europa's radiation environment adds noise, potentially scrambling delicate signals. Enceladus had it easier. Its plumes were dusted with fresh, pristine ice. Europa's material might be older, more processed, or altered by radiation chemistry. What if we find nothing? Even a null result would be profound. It'd suggest Europa's ocean, while vast, might lack the chemical diversity Enceladus enjoys, or that its plumes simply don't carry the goods. But the mere possibility of success has astronomers holding their breath. Imagine a future where we don't just speculate about alien oceans, but taste them one microscopic droplet at a time. Europa's plumes aren't just cracks in the ice, they're windows into the darkest, most mysterious waters beyond our world. Beneath the rust-colored deserts of Mars, buried under a mile of ice at the South Pole, lies one of the most tantalizing discoveries in planetary science, a network of liquid lakes that shouldn't exist. In 2018, the European Space Agency's Mars Express orbiter sent radar pulses through the ice cap, revealing shiny reflections that could only mean one thing: liquid water. Not frozen, not vapor, liquid. The implications were staggering. Mars, a world we'd written off as a desiccated wasteland, might still hold pockets of wetness, places where life, in theory, could cling on. But the plot thickened almost immediately. These aren't your typical alpine lakes. The temperatures at Mars's South Pole hover around -68 degrees Celsius, far too cold for pure water to stay liquid. The answer: salt, lots of it. Dissolved salts like magnesium and calcium perchlorate could act as antifreeze, lowering the water's freezing point dramatically. Picture a thick, syrupy brine, more like a cold slurry than the lakes we know on Earth, trapped under crushing pressure and eternal darkness. Some researchers argue the radar signals might not even be liquid at all, but a sort of waterlogged sediment, a half-frozen mush clinging to mineral grains. The debate rages because the stakes are so high. If it's liquid, even a harsh, salty soup, it rewrites the playbook for where life can exist. Here's where missions like NASA's proposed ice mapper come in. Future orbiters could use advanced radar to scan these lakes in higher resolution, mapping their contours and even estimating salinity. But the real game changer would be a lander capable of drilling through the ice, a technological feat akin to Antarctica's Lake Vostok expeditions, but on another planet. Imagine a robotic drill melting its way down, inch by painstaking inch, until it breaches the hidden reservoir. The challenges are monstrous. The drill would need to avoid contaminating the lake with earthly microbes while surviving temperatures that turn metal brittle and electronics sluggish. Yet the payoff would be historic. Sampling that brine could reveal organic compounds, or dare we imagine actual microbial Martians adapted to the darkness, the cold, the salt. These wouldn't be little green men. They'd be extremophiles unlike anything on Earth, possibly relicts from a time when Mars's seas still rippled under a thicker atmosphere. Or perhaps the lakes are sterile, their chemistry too hostile even for the hardiest life. Either answer is profound. Sterility would suggest that liquid water alone isn't enough, that life spark needs something more. But if we find even dormant cells in that frigid brine, it would mean life isn't just an earthly accident. It's a cosmic inevitability waiting wherever the faintest whispers of habitability linger. Mars's underground lakes are more than scientific curiosities, they're time capsules, holding secrets from when the planet was young and wet. Every new radar ping, every debated dataset brings us closer to answering the oldest question of all: are we alone? Or is the universe humming with life in places we're only beginning to dare explore? On August 15, 1977, a radio telescope in Ohio picked up a signal so bizarre, so inexplicable, that the astronomer who discovered it scrawled, "Wow." In red ink on the printout, for 72 seconds, a narrowband radio burst precisely the kind theorists predicted an alien civilization might use blazed across the sky near the constellation Sagittarius. Then, just as suddenly, it vanished. Decades later, the wow signal remains astronomy's most tantalizing ghost. No natural phenomenon matches its profile, not pulsars, not comets, not cosmic interference. It came from nowhere, it left no trace, and it forces us to confront a chilling possibility. What if, for one fleeting moment, we intercepted someone else's cosmic hello? Fast forward to today, and the hunt for such signals has evolved from a solitary blip on a printout to a full-scale scientific operation. projects like Breakthrough Listen deploy some of Earth's most powerful telescopes, from Green Bank in West Virginia to the Parkes Observatory in Australia, scanning millions of stars for similar anomalies. Unlike the passive listening of the past, modern searches target specific star systems, including those hosting potentially habitable exoplanets like Proxima Centauri b and TRAPPIST-1e. The logic is simple. If life thrives on these worlds, could their civilizations be sending out signals we just haven't tuned into yet? But let's pause on that word, technosignatures. Unlike biosignatures, the chemical fingerprints of life, technosignatures are the hallmarks of technology. They could be narrowband radio waves like the WOW signal, laser pulses flashing like interstellar Morse code, or even megastructures blocking starlight in unnatural patterns. Here's the twist: the same cosmic wonders we've explored, Europa's ocean, Enceladus's plumes, Titan's methane lakes, might not just harbor life. They could be the sources of these signals. Imagine a subsurface civilization on Europa, their radio transmitters bolted to the ice ceiling, broadcasting through cracks into space. Or a hyper-advanced society on an ancient Hycean world, using orbital lasers to communicate across star systems. The challenge is separating cosmic static from cosmic conversation. Every day, Earth's telescopes drown in false alarm satellites, quasars, even microwave ovens polluting the data. Breakthrough Listen filters this noise with machine learning, flagging only the anomalies that defy natural explanation. Yet even their sensitivity has limits. A signal beamed directly at Earth would be easy to spot, but most alien broadcasts, assuming they exist, would likely be omnidirectional, bleeding energy into space like a lighthouse beam fading with distance. By the time they reach us, they'd be whispers lost in the galactic wind. That's where the WOW signal taunts us. It originated near a star called Chi Sagittarii, a sun-like star with no known planets. But what if it wasn't from the star at all? Interstellar probes, like our own Voyagers, could theoretically relay signals from much farther away. Or perhaps the burst was a one-time event, a dying alien satellite, a misaligned beacon, or even a message we lack the context to decode. The signal's brevity is its greatest riddle: 72 seconds of perfection, then silence. Was it a fleeting test, a distress call, or just cosmic static playing the ultimate prank? The deeper lesson isn't about one anomaly, it's about scale. The WOW signal happened 46 years ago in a universe 13 billion years old. If civilizations are out there, their timelines might not align with ours. Their signals could be rare, sporadic, or encoded in ways we've yet to imagine. Breakthrough Listen isn't just scanning stars, it's sifting through time, hunting for needles in a haystack light years wide. Every unexplained blip, whether from a red dwarf's habitable zone or the voids between galaxies, carries the same electric question: are we listening closely enough? So when we peer at Europa's icy shell or Titan's hazy skies, we're not just looking for microbes. We're wondering if, beneath those alien landscapes, someone might be looking back, and whether someday another telescope will catch a signal that doesn't say "wow," but something far clearer: hello. From the hidden oceans of Europa to the methane rivers of Titan, from the ancient shores of Mars to the diamond-crusted remnants of pulsar planets, we've journeyed through 25 cosmic wonders where life in forms familiar or utterly alien might just be waiting. The universe isn't a barren wasteland, it's a sprawling mosaic of possibilities, each world rewriting the rules of what habitable even means. Ice-covered moons with subsurface seas, rogue planets drifting through the void, super-Earths bathed in eternal twilight. Every discovery shatters our assumptions, proving that life's potential is as boundless as the cosmos itself. Humanity's quest for answers is far from over. In the coming years, missions like Europa Clipper and Dragonfly will plunge into these alien environments, sniffing plumes, drilling ice, and scouring dunes for the faintest whispers of biology. Telescopes like JWST and the upcoming Habitable Worlds Observatory will dissect the atmospheres of distant exoplanets, hunting for chemical imbalances that scream life. This isn't just science, it's a collective leap of curiosity, a refusal to accept that we're alone in the silence. So now it's your turn. Look up at the night sky and wonder, which of these cosmic marvels do you think holds the key? Is it Enceladus with its geysers spewing ocean samples into space? Or Proxima Centauri b, a neighbor so close we might one day knock on its door? Maybe it's a dark horse, a rogue planet, or a pulsar world where life thrives in ways we've yet to imagine. The debate isn't just academic, it's a celebration of how vast, how strange, and how alive our universe might truly be. Drop your pick in the comments, and let's keep the conversation as infinite as the stars. After exploring 25 cosmic wonders where life might thrive, one question remains: just how many alien civilizations could be out there? This isn't just speculation, it's a math problem. Enter the Drake equation, a deceptively simple formula crafted by astronomer Frank Drake in 1961 to estimate the number of detectable intelligent societies in our galaxy. At first glance, it looks like a string of variables, but each term holds a universe of possibilities, directly tying into the worlds we've just explored. Take the first variable, the rate of star formation. Our Milky Way churns out about 7 new stars per year, each a potential host for planets, but not all stars are created equal. Red dwarfs like Proxima Centauri outnumber Sun-like stars 10 to 1, yet their violent flares might sterilize nearby worlds. Orange dwarfs, calmer and longer-lived, could be the sweet spot. Planets like Kepler 442b orbit these stable stars, offering prime real estate for life. The equation's next terms delve deeper. What fraction of stars have planets? Thanks to Kepler and TESS, we now know nearly every star has at least one world, with many nestled in habitable zones. Then comes the crux: how many of those planets actually develop life? Europa and Enceladus suggest liquid water isn't rare, just hidden. Mars proves even desolate worlds might cling to subsurface oases. Titan's methane chemistry hints that solvents beyond water could brew biology. Each wonder we've covered tweaks this variable, nudging the odds up or down. The equation's later terms get even thornier. If life emerges, how often does it evolve intelligence? Earth took 4 billion years to produce a technological species, but Teegarden stars' planets have had billions of extra years to experiment. Could civilizations rise and fall before their stars even flicker? The final variables, how long intelligent societies last, strike a sobering note. A civilization might broadcast signals for millennia or wipe itself out in centuries. The wow signal's fleeting blip reminds us how easily messages could vanish into the cosmic static. Yet the Drake equation isn't about a single answer, it's a framework for wonder. Plug in optimistic numbers and the galaxy hums with thousands of civilizations. Pessimistic estimates, we might be alone. The truth likely lies somewhere between, and every discovery, whether plumes on Europa or methane on Mars, sharpens our guesses. So next time you gaze at the night sky, remember, those twinkling stars aren't just dots. They're variables in the universe's grand equation, each a potential home for life as strange as Titan's methane microbes or as advanced as a civilization harnessing black hole energy. The cosmos isn't just vast, it's vibrating with possibility, and we're only beginning to listen.